This video presents a short introduction and solution to problems related to reservoir depletion and injection. This is chapter number 8 of my notes in Introduction to Energy Geomechanics. All right, so let's go into that. Whenever we change the pressure in a formation, most often due to depletion, we can cause also changes of stresses within the reservoir itself. Here within a schematic of this dotted ellipse, and also outside the reservoir. Sometimes the changes of pressure are so important that they can cause significant deformation of the reservoir layer and adjacent formations that can result in settlement of the surface, a phenomenon called subsidence or subsidence, depending who you talk to, and also can cause induced seismicity near this region. You may think this problem as a problem similar to wellbore stability. If you remember, when we analyzed a problem, we said that whenever we drill a wellbore, we take the rock that was supporting the previous stresses at that place, and now you have to replace that with either a void or the drilling mud, which is applying a pressure on the wellbore. In the case of reservoir depletion, is similar because we're changing locally the stresses within a reservoir, and that change of pressure is going to affect the stresses around the reservoir as well and within the reservoir. The only difference with the wellbore case is that reservoirs are usually much longer in one or two directions than in the vertical directions. And we're going to see that because of that geometrical shape, we're going to be able to use some simplified solutions in order to predict these changes of stresses and deformations. Okay, let's talk before about some generalities, and I'll show you some cool pictures as well before getting into the mathematics of the problem. All right, as we were saying, the problem of reservoir depletion is caused by a decrease of reservoir pressure as a function of time because of the extraction of a fluid. This can happen in a conventional reservoir, like for example the sandstone, or it can happen in an unconventional formation like this source rock over here. Both of them are reservoirs in which if you decrease the pore pressure, the effective and total stresses are going to change with time as a function of that change of pore pressure. Sometimes these changes of pressure are so large that they can induce significant deformation. And here I have an example about that. This is a great web page, a great summary about the consequences of subsidence whenever the problem is not very well controlled. But in this case, it did control it after some time. So I'm going to provide this link over here, and you will see that it's a very nice guide. It has some very nice pictures. All right, so this is the case of Long Beach, California. At the beginning of the 19th century, this place was recognized to have massive amounts of oil, and therefore extraction of oil started at that time. But however, what they didn't recognize at that time was that this extraction of oil was causing a significant subsidence of the surface. So you can see here near the city of Long Beach that there were settlements of the surface of up to more or less 30 feet, which is quite large. And and keep in mind also the size of the influence of this subsidence problem, that it's several miles long. And we're going to see the equations that help us explain this type of behavior. But before we go that, let's just see cool pictures over there. You can see that whenever the surface started to to sink, then they started to have problems of water getting into the roads, and they got very severe after some time. And here you can see how in some places the subsidence or the surface went down so much that the wellheads were basically just left alone on the surface. Right here you see the conducting casing and the wellhead over here, which is quite above what it was originally before beginning the extraction of oil. And here you also have a nice picture about that, about how dramatic this the settlement of the surface was at this particular location. So the solution for this case was to repressurize the reservoir by injecting water so that the surface would not sink anymore. Because if they continue to lower the pressure, very likely they will have even more settlement or subsidence. And they did that by, as I was saying, by injecting water from a location near Long Beach. And if you ever go to Long Beach, you're going to see these islands, that this is how they look from the shore. I remember about 2 years ago, I went running around this area in Long Beach, and here's a picture from the top, and what you can see is all the oil facilities, and from the outside it doesn't look so, and just for landscaping they decorated that as an island with some towers. But this is basically an oil facility, and it's a controlled oil facility right now because they stopped the subsidence by injecting water. But coming back now to the theory and to how to solve this problem, what happened in this particular case is that they lowered the pore pressure too much, the rock was relatively soft, and also the reservoir was quite thick. So a combination of that caused this significant subsidence. All right, let's see how we address this problem. We can simplify this problem to what we have seen already, and is known as a uniaxial strain compaction stress path, in which we assume that there are no strains in the horizontal direction, here directions 1, 2, and there is just strain in the vertical direction. In this case, this is going to be strain epsilon 3, 3. The decrease of pore pressure is going to cause changes of stresses, and it's going to cause changes of strain. And we'll utilize this equation in order to see how we predict those changes of stresses with this simplified analysis. Before we get into the actual equations, let's see what is going to be the influence of that. Why do we want to predict these cases of subsidence? There are two basic applications. One is going to be, well, actually three. One is going to be to avoid significant subsidence, because this is going to cause problems in your surface facilities, either onshore or offshore. Also, they are going to cause problems to the casing. Second, when you decrease the pore pressure too much, and if the effective stresses increase too much, also the porosity of the rock or the width of the fractures, if this is a fracture formation, like for example in an unconventional formation, is going to decrease. Therefore, the permeability is going to decrease too. And third, also we're going to have problems related to induced seismicity if the deformation is too much, or reactivation of faults that may not necessarily lead to seismicity, but that may lead to problems like case shearing on some adjacent facilities. All right, so here we see the problem of permeability, and we're going to see that the decrease of pore pressure is going to lead to increase in effective stresses, and that's going to cause a decrease of porosity of the rock or a decrease in the fracture width if we have a fracture formation. Both of those, a decrease in porosity and a decrease in the pore size are going to cause a decrease in permeability and also a decrease in the fracture width. But the effect of decreasing fracture width is going to be much more severe in permeability than the decrease in the pore size. Why? Because the permeability in fracture formations is proportional to the cube of the fracture width. So if we just decrease a little bit the fracture width, permeability is going to suffer a lot. And this is actually a problem in unconventional formations, in which as we start depleting, the fractures close. Sometimes even those that were propped, they start to close and embed some propant, and the fracture permeability decreases sharply, and so does the production. So in order to avoid that, it is important to take into account this phenomena. For the case of the porous formations with mostly pores instead of fractures, there is also a limit in which we might start crushing the pore space and the grains because of increased effective stress. And here you have an example of that. If you increase too much the effective stresses by lowering the pressure too much, you might cause a rock that looks more or less like this, with nice and open pores, to look something like that. With after grain crushing, we see that the pore size is significantly smaller than what we had before. And that, of course, is going to cause significant decreases in permeability as well. Okay, so now that we have seen the applications, let's see how we solve this problem. In order to solve this problem, we're going to appeal to what is called the theory of poroelasticity. And in the theory of poroelasticity, we're going to expand the effective stress equation to what is known as the Biot effective stress. If you remember before, we said that effective stress is equal to total stress minus pore pressure. In the corrected effective stress equation, we add another parameter, which is a parameter alpha, which is called the Biot coefficient. The Biot coefficient goes from a value as a lower bound to be equal to the porosity to a value with upper bound, which is going to be 1. Usually very porous and soft formations have a Biot coefficient which is closer to 1, while tighter formations have a Biot coefficient that gets closer to 0.5 or 0.6, depending on the rock. All right, with this new effective stress equation, we're going to correct the effective stress in order to calculate it more accurately for changes of pore pressure, introducing this Biot coefficient. This is a more refined version of the effective stress equation that we used before. But basically, the only thing that we have to do is to multiply pore pressure times this coefficient, which is called the Biot coefficient. And that's what I do in this equation over here. So here we have effective stress is equal to the stiffness matrix times strain. And I have already implemented the boundary conditions in which there are no strains in horizontal direction, and I only allow for strain in the vertical direction. So when I do that, I can solve for the variation of horizontal stresses and the variation of the effective vertical stress with pore pressure. Basically, the only thing I do is just multiply rows times columns in order to get the equations that follow. For example, the first equation is the result of multiplying the third row times this column, and as you can see, since all of these are 0, the only part of the equation that's going to survive is going to be the one that has epsilon 33, and that's going to be multiplied by 1 minus Poisson ratio times that common factor, which is what you see over here. One more clarification that I see right here. Remember that shear strains are also equal to 0 in the uniaxial strain assumption. All right, With this equation now, what we can do is we can predict what is going to be the elastic strain caused by a change in pore pressure in the formation. And notice that in this equation, these are material parameters. Young modulus is going to be mostly constant. Poisson ratio is going to be constant. And the same for the Biot coefficient. The pore pressure is going to vary. And what about S33? S33 is the total vertical stress. And we're going to assume, based on our schematic over here, that S33, the total vertical stress, is not going to change. Basically, what we're saying is that even if I change the pressure in the reservoir, the total weight of the rock on top of the reservoir is not going to change. And that it's a good assumption, especially if your cap rock is relatively soft, so it cannot take any stresses as this material in the reservoir deforms. And that's what we're going to do. Just to simplify this equation, we're going to assume that the total vertical stress is not going to change. And remember, this is just the total vertical stress. Therefore, in this equation, S23 is going to be a constant. And what that means is that the change in vertical strain is going to be proportional to the change in pore pressure, multiply the Biot coefficient, and divide the constraint modulus, where the constraint modulus is this factor over here. And it's something that we already saw before when we were talking about the compressibility of rocks. Something important to mention now is that this equation can capture only elastic strains. But with depletion, most times what we see is that serious deformation comes from plastic deformation. And this is also seen in this particular figure, in which if we, for example, wanted to model the strain which is caused by grain crashing, that I'm not going to be able to do that with the equations that I shared with you before, because those equations just capture the elastic strain, mostly in this part. There is going to be a typical or a given stress, which is called the yield stress, at which if I surpass that stress, I'm going to incur into significant plastic strains which are not recoverable. Those are not taken into account in this equation, but you can take them into account with more advanced models. All right, but for now, let's just limit ourselves to this simple equation with the elastic deformation. And this is one of the equations that we wanted, because we wanted to predict what would be the strain caused by deformation of the reservoir caused by the change of pore pressure. And here we see the equation, which is equation 8.4. Another problem that we want to solve, and another quantity that we want to predict, is going to be what are going to be the variations of effective stress within the reservoir, and also the variations of total stress within the reservoir. Let me tell you why this is going to be important. Whenever a reservoir is depleted, the pore pressure is going to decrease. And we said that the total vertical stress is not going to change. However, the horizontal total stress might change. And how that total horizontal stress changes is going to affect the fracture grading through this formation. For example, if I were to deplete this sandstone reservoir and I get to a pressure in the reservoir which was much lower than before, and then I try to drill another wellbore that goes through that sandstone reservoir looking for the source rock, when I pass through this depleted formation, the state of stresses is not going to be the same as what it was before depleting the reservoir. Actually, the total horizontal stress is going to decrease. And that decrease of total horizontal stress, if we are in a normal faulting or in a strike slip regime area, is going to cause a decrease of the fracture gradient, so that when I drill to that formation, I might encounter problems of low circulation, because as soon as I hit this formation, the weight of the mud might be enough to overcome the least principal stress, which in this case is going to be horizontal, and cause an unintentional hydraulic fracture within this formation. And this is something that we have seen before, but now you can see the reason right away of drilling through depleted formations where the pressure is still low. So how do we predict that decrease in horizontal stress? And this is what we're going to do over here with these same equations, but now with equation 1, or you can do it with row number 1 or with row number 2. It's going to be the same equation. I can solve for what is going to be S11 as a function of the change of pressure, also utilizing equation 8.4. And when I do that, when I combine these three equations, I arrive to this equation over here that tells me what is going to be the variation of the total horizontal stress with the variation of pore pressure in the formation. And that's going to depend on the Biot coefficient and on the Poisson ratio. That coefficient is a coefficient called coefficient A, and it typically varies from 0.5 to 0.9, and help us understand how the total horizontal stress is going to vary with the change of pore pressure. Notice that in this case, if the pore pressure decreases, the total horizontal stress is going to decrease. And this is what we can see in theory and also in actual measurements in the reservoir. Here what we're doing is we're plotting on the y-axis total stress and on the x-axis reservoir pressure. So the initial condition at the high reservoir pressure is, let's say, somewhere over here. Initial pore pressure PP0 and final pore pressure PPF. At the initial conditions, I have a given total vertical stress and a given total horizontal stress. As time passes by and reservoir pressure decreases, going to the left, what I have is, as I assumed before, that the vertical stress is not going to change, but the total horizontal stress will change. And the decrease of total horizontal stress is going to depend on the change in pore pressure through this parameter A that we saw over here. And basically, as we see, the total horizontal stress is going to decrease as we change the reservoir pressure. And you have on the right field evidence for this type of behavior in the North Sea, where we can see variations of the minimum horizontal stress as a function of reservoir pressure for reservoirs. It's actually the same reservoir, but in different areas, where pore pressure decreases from more or less 45 MPa to 25 MPa. That's a 20 MPa change of pore pressure, a 3000 psi change of pore pressure, which is a quite decent change of pore pressure. And we can see that that can cause changes of horizontal stress, which are also quite significant, in the order of 15 megapascals. And you can imagine that those changes in stress of 15 megapascal, which is somewhere around 2000 and 3000 psi, is going to affect the fracture gradient also significantly. All right. One more thing that we can do is also predict the changes in effective stress. As we were saying, the change of pore pressure is going to lower the total horizontal stress. But don't be fooled, because that doesn't mean that the rock is going to feel less compression. Actually, it feels more compression, because this is given by the effective stresses. And the changes of effective stress are positive. If you decrease the pore pressure, both the effective vertical stress and the effective horizontal stress are going to increase. And we can see that very nicely with this more circle example. Let me just get all here within the browser, that if my initial condition is somewhere over here, sigma h mean and sigma b, with a decrease of pore pressure, my vertical stress, effective vertical stress, is going to increase more or less proportional to the pore pressure. Is actually the pore pressure times the Biot coefficient, so a little bit less than the pore pressure, and the effective horizontal stress is also going to change. Not as much as the vertical effective stress, but it's also going to increase, and it's going to be proportional to also the Biot coefficient and the ratio of Poisson ratio divided 1 minus Poisson ratio. This is what is going to tell me what is the change of effective stress. But both of them are going to increase, which means that the rock is going to feel more compression after depletion. And for example, this is why if we had vertical fractures are going to start to close. Why? Because the effective horizontal stress is going to increase. The more that effective horizontal stress increases, the more is going to be the change in the width of the fracture, and the more is going to be the change in permeability in such fracture reservoir. All right, so with this short introduction and this simplified solution, we have seen, let me come back to the top, how we can predict in a formation like this, either in a conventional reservoir or in an unconventional reservoir, what are going to be the deformation expected due to depletion, and also the changes of stresses within deformation expected due to depletion. And we have seen that horizontal stress, total horizontal stress is going to decrease, but effective horizontal stress is going to increase. And that increased compaction within the rock is going to cause decreases of permeability. Just to finish this lecture, I encourage you to check problem A1, in which you're going to have to calculate what is the deformation of the reservoir in a particular location with all the parameters, poroelastic parameters that characterize that formation, and the change of pore pressure at that particular location. This reminds me something. At some point at the beginning of the class, we talked about casing buckling. The phenomenon of casing buckling occurs because of the drag of the reservoir rock on the casing, that if the reservoir deforms too much, the casing is going to be dragged to deform in the same way, and usually casing is much stiffer than rock, so the casing is going to take this drag force that is going to cause the casing to buckle. But we're not going to calculate this in this class, but remember this is related to that. All right, so in this problem, what I ask you to do is, with all these given parameters and this change of pore pressure, to calculate the settlement of the top of the reservoir, or the vertical displacement of the top of the reservoir. Also, with these properties, you can calculate the pore pressure compressibility. I encourage you to take a look at chapter number 3 in order to see this equation. It's also explained briefly above in this chapter. Also, you can calculate the total horizontal stress change, the changes of effective stresses, vertical and horizontal, and also assuming a permeability law for this particular formation. This is a typical permeability law for a fracture formation. You can also calculate what is going to be the change of permeability because of the increase in effective horizontal stress. And you're going to see that basically, as you increase the effective horizontal stress, the permeability is going to sharply decrease. And you're going to see the solution over here step by step. And that's something that I encourage you to look at, and that also I'm going to evaluate in my quizzes.